Hello and welcome to tutorial number 3. Our topic today is chemical versus physical change and classifying matter. Before we get started, I do really quickly want to remind you that the notes to accompany each and every tutorial can be found from my website. This tutorial in particular has a lot of definitions, so probably a really good set of notes to keep in front of you while you're going through this video so that you're not frantically writing things down, trying to get all of those definitions. Okay, with that said, let's get started with matter. Matter can be defined as anything that has mass and occupies space. So really, matter is anything that you can think of in your world. It is the food that you eat, the clothes that you wear, the air that you breathe, the pencil that you're writing with. These are all examples of matter. And chemistry is the study of matter and the changes that matter undergoes. So it is very important in an introductory chemistry class to make sure that you know how to correctly classify matter. Okay, we're going to go ahead and start off with the 3 states of matter. And just do a quick definition for solid, liquid, and gas. Okay, solids have a fixed volume and a fixed shape. And the particles that make up a solid are held together in a very tight, organized structure. So I'm just going to make a little picture here indicating some particles with a nice, tight, organized structure. Okay, so there's a pretty significant attractive force between the particles that make up a solid. Oh, let's write one more thing. We represent, or we abbreviate solid in chemical equations with a lowercase s in parentheses, like this. Let's write that. All right, now let's go on to liquids. Liquids also have a fixed volume, but no fixed shape. A liquid will take on the shape of the part of the container with which it is held. So a fixed volume, but no fixed shape. Okay, so what we mean by that is if you had a liquid, let's say in a beaker, okay, so let's say you had 50 milliliters of some liquid in a beaker, and then you poured that into a graduated cylinder. Well, it would take on the new shape of whatever portion of the graduated cylinder that it was contained in, but it would still be the same volume. It would still be 50 milliliters of that liquid. Okay. The particles of a liquid are also held close together and have significant attractive forces for one another, but they are able to slide past each other and they have a little more freedom in that movement, and so liquids have flow, which we're familiar with. And we abbreviate liquid with a lowercase l in a chemical equation. And last but not least, gases have no fixed volume and no fixed shape. A gas will take on the entire shape of the container which holds it. So no fixed volume and no fixed shape. Okay, so if we had a gas, let's say it's in a stoppered Erlenmeyer flask here. Make some dots to represent my gas. Okay, so I'll spread out in that Erlenmeyer flask. There would be a lot of empty space between those particles. So I'm just going to use some green here to represent all this empty space between these particles of the gas. So a gas is mostly empty space. And that's what makes those gases highly compressible and expandable. And also, there are no significant attractive forces between the particles of a gas. Okay. And we would abbreviate a gas in a chemical equation with a lowercase g, like that. All right, so just a real quick introduction to these three states of matter, and now we're going to go on to classifying matter. All right, so we're on slide 3 of the notes, classifying matter. Kind of messy there. Erase that. Okay, classifying matter. All right, so matter is a very vague term, really. We said matter is anything that has mass and occupies space, a very vague term. Matter can be further subcategorized as being either a pure substance, I'm going to make a little flow chart here, or a mixture. It's one or the other, it's not both. Okay, so let's talk about pure substances first, and I'll put some definitions down below my flow chart as we go. Pure substances. Pure substances have a fixed composition and distinct properties. And what we mean by a fixed composition is that, let's take an example like water. Okay, for example, water is made up of 2 hydrogen for every 1 oxygen. And that's why when we write the formula for water, you've probably seen before, that it's written as H2O. Well, that's the fixed composition for water. Always a 2-to-1 ratio of hydrogen to oxygen. A different substance might have a different ratio of hydrogen to oxygen, like let's say 2 hydrogen to 2 oxygen. That will be a completely different chemical substance. That would actually be hydrogen peroxide, and it would have completely different chemical and physical properties when compared to water, okay? Because it would be a completely different chemical substance. So that's what we mean by a fixed composition. Water, in order to be water, it's always got to be this ratio. It has a fixed composition. Distinct properties, what we mean by distinct properties is things like its melting point, its boiling point, its color, its density, things like that. So water, we can look up a whole slew of chemical and physical properties for water. Let's just write a few down here. It has it's a clear, colorless liquid at room temperature anyway, atmospheric pressure. It has a melting point, I'll just write MP for melting point, of 0 degrees Celsius. It has a boiling point, I'll just write BP for boiling point, of 100 degrees Celsius. Its density is 1.00 grams per milliliter, okay, etc. So that's probably enough for its different properties. But you can see that it has its own unique, distinct properties. Hydrogen peroxide, which is 2 hydrogens to 2 oxygen, would have completely different chemical and physical properties of its own. Okay. Let's do one more example, just to really solidify this. Let's use another example that I think you'll be familiar with. Let's do table salt, or sodium chloride, which is made up of 1 sodium ion for every 1 chloride ion. Okay, so that's why we write the formula for sodium chloride as NaCl. It's 1 to 1. Okay, never 2 to 1, never 1 to 2. It's always 1 to 1. Fixed composition for this pure substance. And we could also go on and write a bunch of properties for sodium chloride. It has its own distinct properties. Let's write a few. We know that sodium chloride, table salt, is a white crystalline solid. Its melting point is really high. It's 801 degrees Celsius. Its boiling point is, of course, even higher than that. It's 1,413 degrees Celsius. Its density, not sure if you can see this low on the board, hope you can. Its density is 2.16 grams per centimeter cubed. And again, we could go on, but I think that probably gets the point across. It is a pure substance, it has a fixed composition, and it has its own unique, distinct properties. Okay. So let's erase all of this information down here for pure substances to give ourselves some more room, but I'm going to keep this flow chart going. I'm going to add to it, so I'm not going to erase that. Okay, so a pure substance can be further subcategorized as being either an element or a compound. Okay. Let's talk about elements first. Okay. Elements are the basic building blocks from which all matter is formed. Okay, so I'm going to write basic building block for matter. And if you want to see an example of an element, all you have to do is look at a periodic table. This is pulled from tutorial number 4, so if you want to go to the notes for tutorial number 4, you'll find a periodic table there. You can look in your textbook, you can look online, lots of periodic tables. You have access to lots of different periodic tables out there. So if you look at a periodic table of the elements, you will see that there are currently 115 known elements. So I'll write currently 115 known, although I think my periodic table is a little out of date. I don't think it actually shows all of those, but if you've got a really up-to-date periodic table, it would show 115 currently known elements. Now if you took the smallest piece of an element that could exist and still retain the properties of that element, you would have one atom of that element. And an atom is composed of subatomic particles, protons, neutrons, and electrons. And protons have a positive electrical charge, so I'm going to write a little plus there. Neutrons are neutral, I'm going to write 0 for the charge there. And electrons have a negative charge, I'm going to write a negative there to remind you of that. I'm just going to do a real brief introduction to atoms today because we're going to be talking about atoms a lot more in tutorial 4. So just a really quick introduction here today. The protons and the neutrons are all contained in a dense central core known as the nucleus. And then outside of that, in the more voluminous part of an atom, you'll find the electrons zipping around. So let me go to a different color here. Maybe this will stand out a little bit better. Okay, this is to represent the nucleus, the dense central core of an atom, which contains the protons and the neutrons. And then outside, let's go to an even different color, outside of the nucleus, in the more voluminous part of an atom, that's where you will find the electrons. Again, they're zipping around rapidly outside of the nucleus within an atom. Okay, again, just a quick introduction there. We'll talk about that in more detail when we get to tutorial 4. So I'm going to erase elements. Okay. And before we go on to compounds, let's just look at our periodic table, whatever periodic table you have in front of you, and write down a couple examples of elements up here in our flow chart. So I'm just going to pick a couple that I think you'll be familiar with. Helium is an example of an element. Carbon, sodium, and then I'll just write C, periodic table. Okay, there's a bunch more examples in the periodic table. 115 total. All right, compounds. Compounds form when two or more elements combine in a fixed ratio. Of course it's a fixed ratio, right? Because we already said that pure substances have a fixed composition, so it shouldn't surprise you that compounds have a fixed ratio of those elements which make it up. Okay, so let's write here, form from two or more elements combined in a fixed ratio. Okay, so we already saw a couple examples of that with water and with sodium chloride. So let's just take a look and kind of write out a beginner sort of chemical equation for that. So for water, we already saw that that's H2O. It forms when hydrogen combines with oxygen. Okay, so hydrogen, I'm going to write it out. I'm not going to use chemical formulas yet because it's a little premature to do that. Combines with oxygen. Hydrogen is an element, oxygen is an element. These two elements combine to form a compound, water, okay, which is H2O. We know it has a fixed composition of 2 hydrogens to 1 oxygen. Let's also do the other example, sodium chloride, or table salt, which we already saw has a 1-to-1 ratio, NaCl. Okay, so sodium chloride forms from sodium, the element sodium, reacting with the element chlorine to form the compound sodium chloride. And one more thing I want to point out here before we go on, the compound does not have the same properties or even related properties necessarily to the elements which it came from. Okay, so this is a great example of that, because if you look at the chemical properties and physical properties of sodium metal, it is a grayish solid. It's fairly soft and easy to slice. It is highly reactive. It's always stored in an inert oil because of this. It will react just with water. It's a highly reactive metal. Chlorine gas is a yellowish, highly reactive gas, but you put sodium and chlorine together and you get something that is not highly reactive at all. It's a white crystalline solid. It's something we sprinkle on our food and eat. Okay, so notice that the properties, chemical and physical properties of the compound do not relate or come from the chemical and physical properties of the elements which make it up. It is its own unique pure substance with its own distinct properties. Okay, so let's go ahead and erase all of this and keep our flow chart, of course, because we're not done with it. We've got to add to that. Okay, so compounds can be further subcategorized into molecular compounds. I'll just write comps because I'm kind of running out of room there. And ionic compounds. Again, I'll just write comps for compounds because I'm running out of room. Molecular compounds, let's talk about those first. Molecular compounds form when elements combine by sharing their electrons, and therefore they form uncharged particles called molecules. All right, here, elements combine to form uncharged units known as molecules. Okay. And typically this happens when nonmetals react with other nonmetals. So I'm going to write that here. Typically nonmetals only. Let's write a little separation there. Okay. All right, so if you go back to those two examples that we already used for compounds, water and sodium chloride, well, you could check your periodic table and see which of those are classified as metals and which are classified as nonmetals, and you'll see that hydrogen and oxygen are both nonmetals. So when hydrogen and oxygen react to form water, not surprisingly, it forms a molecular compound. Water is a great example. Let's write this in a different color. Of a molecular compound. So I'm going to write that up here as an example for our flow chart. Okay. Ionic compounds, on the other hand, form when one atom transfers its electrons to another atom, and therefore you end up with positively and negatively charged ions. Okay. Elements combine to form charged particles called ions. And this typically happens when metals transfer their electrons to nonmetals. So I'll write that here. Typically, metals and nonmetals. So if you check your periodic table, which should have metals separated in color from the nonmetals, you'll see that sodium is a metal and chlorine is a nonmetal. And so sodium chloride is a good example of an ionic compound. Okay, so I'm going to go ahead and write that up here for an ionic compound. And this is something that we will be talking a lot more about as we get to tutorials. I think it's more like 5 and 6. Okay, so just a little foreshadowing of things to come there. Okay, I'm going to erase all of this about compounds. Mixtures form when two or more pure substances are mixed together. So I'm going to write here 2 or more pure substances mixed. Okay, and mixtures are variable in their compositions and their properties. So very important note here, variable in composition and in their properties. Okay, so let's explain a little bit what we mean by that. Let's say that we have 1 cup of water, okay, and we dissolve 1 gram of salt into that 1 cup of water. Okay, so I'm going to write 5 dots, draw 5 dots to represent my 1 gram of sodium chloride dissolved in that 1 cup of water. Well, another mixture of salt and water might have 2 grams of salt, so twice as much salt in 1 cup of water. Okay, so I'm going to draw twice as many dots to represent that there's twice as much salt in here. Okay, so then if we took a sample from each, same size sample from each, this one would clearly have twice as much salt dissolved in that same quantity of the solution. So variable in their composition. These 2 solutions, even though they're both salt water, would also have different properties. The more salt you dissolve into the water, the higher the boiling point would go, the lower the melting point, the greater the density. Clearly the taste is going to be different. It's going to taste more salty. Okay, so that's what we mean when we say variable in their composition and variable in their properties. So I'm going to erase here. Okay, and we'll finish off this flow chart by further subcategorizing mixtures as being either homogeneous or heterogeneous. Okay. A homogeneous mixture let's write homogeneous mix, is uniform throughout. So I'm just going to write uniform, while a heterogeneous mixture is not uniform throughout. So I'm just going to write not uniform here. So a great example of a homogeneous mixture versus a heterogeneous mixture would be homogenized milk versus unhomogenized milk. Okay. All right, in unhomogenized milk, the fat is in such large globs that a large portion of it is going to separate and float at the top. So you're going to have a layer of cream, a layer of fat on the top. And then you're going to have a layer that's more watery. It's also going to contain some fat and the proteins and all those other things in milk. Okay, but if you homogenize the milk, you have mechanically broken down those larger fat globules so that they will no longer separate out and rise to the top. They'll stay uniformly distributed throughout that solution. Okay, so all of the water and the fat and the protein and all those other things found in milk are evenly distributed in homogenized milk. So your first drink of homogenized milk is going to be the same as the last drink because it's uniform throughout. Whereas your first drink from your unhomogenized milk is going to contain a lot more of the fat and the cream that floats on top, and your last drink is going to be a little more of a watery consistency. Another great example, milk is another great example of that variable composition because we know that we can buy our milk as skim milk or 1% milk or 2% or whole. So again, just another great example of how mixtures are variable in their composition. In this case, they vary in how much fat they contain. Okay, let's go on to our last slide, which is slide number 4. Okay, and the last slide is chemical and physical change. Let's start with physical change. Physical changes are changes that do not affect the identity of the substance that is undergoing the change. Okay, so let's say that we had a sheet of aluminum foil. And we tore that sheet of aluminum foil in half. So now we have 2 smaller sheets, but the identity of the substance is still the same. It's still aluminum foil. So that would just be a physical change. The identity of the substance has not been changed. All phase changes, this is a very important note, all phase changes are just physical change. Okay, so let's write down a few of the more common phase changes that you'll probably run into in your introductory chemistry class. So melting, which is going from the solid to the liquid state. Freezing, going from the liquid to the solid state. Boiling, going from the liquid to the gaseous state. Condensing, going from the gaseous to the liquid state. These are all just physical change. So let's think about that for just a moment longer. But let's say we take an ice cube out of the freezer. Okay, and an ice cube is just water, H2O, in the solid phase. We set that out on the counter, it's going to melt. So that's my representation of liquid water, water in the liquid phase, my drawing for that. Okay, but the substance is still H2O. The identity of the substance has not changed just because the phase has changed. Okay. Last but not least, dissolving. Dissolving is just a physical change as well. So anytime something is being dissolved, it is also just a physical change. Okay, let's talk about chemical changes. With a chemical change, a substance is changed into a different chemical substance or substances. So for example, we talked earlier about sodium chloride, which is made up of sodium and chlorine, the elements sodium and chlorine. Well, sodium chloride can be broken down into the elements that make it up. It can be broken down by a chemical change into sodium, metal, and chlorine gas. Okay. That would be a chemical change because the substance has been turned into, in this case, 2 different substances. And we show our chemical changes through chemical equations in a chemistry class. And that's a big topic for my tutorial number 7. But I am going to just foreshadow that real quick by converting this into a chemical equation, a proper chemical equation. So I'm going to write the formula for sodium chloride, which we did see earlier today. It's a solid. I'm going to go ahead and write the state there. And it's converted in this chemical reaction into sodium, the element, which is also a solid, and chlorine gas, which happens to be a diatomic molecule, which is why I'm writing the 2 there. So if you don't know about that, don't worry, because that'll be something I cover in a future tutorial. And then I'm going to go ahead and balance it. And balancing equations will be covered in tutorial number 7. A proper chemical equation has to be balanced. Okay? All right, so there's a chemical equation for that written out chemical reaction from above. Just a little foreshadowing of things to come. Okay, that concludes our tutorial number 3. Thank you very much for tuning in.